Balancing chemical equations is like chemical bookkeeping. The law of conservation of mass says that matter cannot be created or destroyed during a chemical reaction. What it means for us in terms of a chemical equation is that we must have the same number of each type of element on the reactant side and the product side. That's where balancing comes in. So how I like to do it is by setting up a table and just comparing the different sides of the reaction. So I have the reactants, and I see that I have aluminum, hydrogens, sulfurs, and oxygens. And you should have the same elements on both sides of your equation. And so I just set up a table like this. Tables are not required. It's just a way to visualize what's going on. You can balance equations by inspection, and that would be doing what we're doing in a table in your head. Now, a general pattern that's helpful in balancing equations is that balance metals first, nonmetals second, then hydrogens and oxygens. Now, this is not a strict rule, but it's like the path of least resistance for most chemical equations. The truth is, you could balance any order you wanted, and in the end, you should still have the same number of each type of element on each side. So I'll start with aluminum, and I see here there's 1, and here there's 2. So I would need to put a coefficient in front of the aluminum, a 2, so that now I would have 2 aluminums on both sides. Now I think I'll go ahead and balance sulfur next. So I find my sulfur, and on this side, right there, there's 1. And this sulfur, there's a 3 here, and so that 3 will distribute through, so 3 times 1 gives me 3. So it's not balanced with 1 on the reactant side, so then I would have to put a 3 in front of the H2SO4. So now I've balanced the aluminum and the sulfur. So let's try the hydrogens. So on the reactant side, I have a 3 already in place, and I have to multiply it by the 2, so that's 6 hydrogen. And here I only have 2, so I would have to put a 3 in front of it. So 3 times 2 is 6. Whoops, I didn't mean to draw a line through hydrogen. So there's 6, so that's balanced. And then I would look at the oxygen. Now there's a 3 here, times 4, that's 12. And on this side, the 3 on the outside times 4 is 12. So I didn't have to do anything in the end to balance the oxygen. So the coefficients that I ended up writing, let me erase this equation. So it's a 2, a 3, and a 3. So I had a 2, a 3, and a 3. Now remember, when you're balancing equations, the only thing you can do is put a number in front of the whole formula. So if you have something like the H2SO4, you can't break it apart and put coefficients in the middle. You just put it on the front of that chemical formula. Now I'm going to erase this one, and you can replay it if you need to, but I want to show you another way that you could balance this equation. So if you notice here, sulfate is a polyatomic ion. And so when you have polyatomic ions, you notice it stays the same on both sides. And so you can actually balance that as a group. So instead of splitting the oxygens and the sulfurs, I'll just keep it as a sulfate group. Now, it's not required that you learn how to do it this way, but for some of you, this may make a lot of sense, and it shortens it by 1 element. So then the process would be the same. I would say I have 1 aluminum and 2 aluminums, so I would put the 2 in front. Then this time I'd look at sulfates, and on this side right here, there's only 1 sulfate. On this side, I see the sulfate has a parentheses, and it has a 3. So So what I would need to do is put a 3, and remember I can't put it in front of the sulfate, I can only put it in front of the whole formula, so I'd put my 3 there. Now the hydrogen on the reactant side, I'd take 3 times 2, which is 6. And here on the product side, I only have 2, so I'd have to put a 3. So you see, you still get the same coefficients. I had a 2, a 3, and a 3. There's no number here, which implies that it would be a 1. And so I get the same balancing, but I just balance using the sulfate. So either way, you can try. So let's try this next one. And you might pause the video, or maybe you've already done it and now you're just checking your answers. So I see I have Na, and now I will do this at breaking down individual elements, and then I can show you this one also has polyatomic ions, so we'll do it both ways. So I have Na, I have S, I have O, I have H, and I have P. So I'll start with my metals. Okay, I have 2 here, sodiums, and 3 here. So 6 is the first number those have in common, so I'd put a 3 in front of that and a 2 in front of that. Then I'll do the non-metals, so I'll do sulfur. So I have 1 sulfur here and 1 sulfur here. So, oh, I hope you caught me. I don't have 1 sulfur here. I have 1 sulfur, but I've already put this coefficient, so I have to write that would be 3 sulfurs because it's 3 times 1. And here I do only have 1 sulfur. There's no coefficient here. So that means I'd have to put a 3 there. So now it's 3 times 1. Now I'm going to skip oxygen and hydrogen, go to the other nonmetal phosphorus, and on this side I have 1. And on this side there's 1 in the formula, but there's a 2 on the outside, so I have 2. So I'd have to place a 2 in front of this formula, so it's 2 times that, which would be 2. Now I think I like to do hydrogens before oxygens, but it doesn't really matter. So here on this side, the hydrogens right here I have 6 because it's 2 times 3. And the hydrogens right here I have 6 because it's 3 times 2. And the oxygens I'd have to add up. There's 3 times 3 there, which is 9. And then 2 times 4 there, which is 8. So I have 17. And here I have 3 times 3, which is 9, plus 2 times 4, which is 8, which is 17. So the oxygens and hydrogens balanced after I balance the metals and the nonmetals. So let me erase it so we can just write the coefficients. So it would be it was a 3, 2, 3, 2 after we wrote the coefficients. Now I'm going to erase this one again just to show you, and I'm going to use the polyatomic ions. And remember, you don't have to do it this way, but there could be some of you that find this helpful. So again, I'm going to compare the whole idea with balancing equations, just you're comparing the two sides. So I have sodium. And now this time, because I have SO3 on both sides, that's the only time you can do this. I have SO3, it's sulfite on both sides. I'll balance that. Then I have hydrogens. And then I have PO4 on both sides. So I'll balance the which is phosphate, and I'll balance those as a group. So this is a 2, and this is a 3. So I put a 3 here, that makes 6, and a 2 here, that makes 6. Then, let me erase all those marks so we can see them. SO3, so I have a 3 here, and I'm going to multiply it, so I'd have a 3. On this side, I only have 1, because there's not a coefficient, so I'd have to put a 3 here, and then it would be 3 times 1. Let's do the phosphates next. This phosphate, I only have 1. This phosphate, I would have 2, so I'd have to put a 2 here. And now hydrogens, I have 6 and 6. So you can see again my coefficients are 3 and a 2, and then there's the arrow and a 3 and a 2. So the big thing in balancing chemical equations is to just take each element at a time, only do one thing at a time, balance it by adding coefficients when you don't have the same number on both sides. Once you've done one element, go to the second one, and then keep working your way through. If you make a change that changes something you've already balanced, then you'll have to go revisit that and balance that part again. Now question 3 says, for each reaction below, classify combination, decomposition, single replacement, or double replacement. So we're going to classify them. Now combination is just like it sounds. You have two different things and they come together to make one thing. They combine. Decomposition is really the opposite of that. They decompose or break apart. So you have something that's all together and then it has a reaction and it splits into pieces. So let's see if we can look at the equations and see if we can find combination and decomposition. Well, look here. Here's two pieces and they come together to make one thing. Well, that's like this. Two pieces comes together to make one. So this is combination. I'll just put a C. Now this one, letter B, is not combination because I have two pieces on both sides. And it's not decomposition because the decomposition has one thing and then breaks into two. And let's see, letter C has two things on both sides. So B and C are not combination or decomposition. But now look here, it's letter D. It has one thing on the reactant side and breaks down into pieces. That's decomposition. Now single replacement and double replacement. So in single replacement, I'll just say CSR. You have something that's by itself and then there's another group that is together. And what single replacement does is A kicks out one of those. Now if A is a metal, it's going to kick out B. If A is a non-metal, it will kick out C. So I can write it for both. So if A kicked out B when it was a metal, then B would be all by itself now, and A would be with C. And that would be when it's a metal, because metals kick out metals. If A is a non-metal, then it has to kick out C, because remember, non-metals would be second in position, so A would kick out C. So then C would be by itself, and then you would have B and A together. So they kick out the same type of element that they are. Now, double replacement, which I really did not leave myself any room for, did I? I'll write it up here. This is when it totally switches partners. So A and B are together and C and D are together. And they'll switch partners, and always the two on the outside will be a new combination and the two on the inside. So A will go with D and C will go with B. Now you might wonder why I did not write B in front of C. But that's because you see C is in the front here and B is in the back. They have to stay in their same positions. So it would look like AD and then CB. So if we look at letter B, we see B, if I look here, so this one went with that one. Okay, there you go. Those two go together. And then H is with NO3 and those two go together. So they switched partners. So this is double replacement. Letter C, okay, this is a metal, and metal will kick out the first position. Remember, hydrogen is on the metal side. So zinc kicks out hydrogen. Look, hydrogen is by itself, and now zinc is with the sulfate over here. So this is single replacement. What helps me is really to imagine, like combination means coming together. Decomposition means when I look at it, something's breaking apart. Single replacement means there's something that's single or all by itself, and it will be a different thing on the reactant and product side, but there's always something that's single. And then double replacement, there's not anybody that's single, and just remember they both switch partners. Now, oxidation-reduction reactions are special types of reactions. They're actually quite common, things from bleaching, rusting, any type of thing, combustion, burning in oxygen. And what we're trying to do is identify things that are oxidized and reduced. And there's two definitions, and we can use the first definition on letter A because I see charges, like I see pluses and pluses. So when you see charges, you can use the definition that I say is Leo says Ger. So what Leo says is that the loss of electrons equals oxidation, and Ger says the gain of electrons equals reduction. Now, how will I know with charge? When something loses electrons, it becomes more positive, right? And we gain electrons, it becomes more negative. So I'm going to look at the charges. So here I'm comparing magnesium on the reactant side, and if it's just the metal, it means it has a 0 charge. And on the product side, it's Mg with a 2+. So do you see it goes from 0 to 2+? That means it's becoming positive. That means it's lost an electron, and so it's oxidation. So magnesium is oxidized. Now, when you're oxidized, you also could be called the reducing agent. Now, I hope you've looked at the videos before you're just trying to answer these questions, because I'm not going through all the details, but there are all details in the videos. Now, let's look at hydrogen. So this hydrogen is an H+, and I don't have to worry that there's 2. And it's going on the product side to H2, which doesn't have a charge, so it's 0. So if I go from a plus down to a 0, it means I'm getting more negative. I have to be gaining electrons to going from a positive 1 down to 0. So if I'm gaining electrons, it's reduction. So the H+ is reduced. It would also be called the oxidizing agent. Whoops. I'm not spelling oxidizing. There we go. Now notice that it's only the reactants that we label. We have to look at the products to see what's happening, but we are only labeling the reactants. The other thing I want to mention, as soon as I knew that magnesium was oxidized, I would have to know the other reactant, or H+ is reduced, because oxidation and reduction always occur together. Now, if I'm looking at example B, I don't see any charges. And when you don't see any charges, then you can't use the Leo says Ger, so this isn't going to work. You have to see charges. So the second definition has to do with oxygens and hydrogens. And I know that oxidation, and I think of oxygen, means that something gains oxygen and or loses hydrogen. And if you're reduced, you're the opposite of that. That would mean you'd lose oxygen or gain hydrogen. So then I have to look at what are these reactants doing. So here's my carbon right here. And as I look at what my carbon chemical did over here, so it's going to there. So here I see it has 4 hydrogens. Here we have 4 hydrogens and 1 oxygen. And on this side I have 2 hydrogens and 2 oxygens. So what did I do? I went from 4 hydrogens to 2. So I lost hydrogen. And I went from 1 oxygen to 2. So I gained oxygen. So that means the CH3OH was oxidized. Also, we could call it the reducing agent. Now O2, if I look at O2, it's going over to H2O. So let's see, this has 2 oxygens. This one has 2 hydrogens and 1 oxygen. So it looks like I gained hydrogen because I went from 0 to 2, and I lost oxygen because I went from 2 to 1. So oxygen is reduced. It's also an oxidizing agent. Oxidizing agent. Now I'll tell you something that I always remember, and this helps me, and maybe it would help you. Oxygen is always an oxidizing agent. And so if I know that oxygen by itself is always an oxidizing agent, I could have solved this by knowing that. Because I would know that I would see oxygen, and then I would know that it must be reduced. And if oxygen is reduced, then the CH3OH must be oxidized. Now the other part, and the last part of chapter 5, has to do with converting between moles and molecules and grams. And there's really 2 tools that we use here. We can use Avogadro's number, which tells us that there are 6.02 times 10 to the 23rd, some type of particle, something small, in every mole. So that's one tool we can use. And then the second tool we can use is molar mass. Now molar mass has to be found on the periodic table. Avogadro's number will be the same for whatever problem you do, but molar mass would change depending on the chemicals. So let's see how we might solve this problem. So first of all, I see that the question is moles. Now, so I want to find moles, and here I see that I'm given molecules. Okay, molecules indicate to me that I'm going to be using Avogadro's number. The molar mass has units of grams per mole, and so the only tool that I have that has molecules in it was Avogadro's number. So this is like a conversion problem. I'm going to take how many molecules I was given and write it down. And to go from molecules to moles I'm using Avogadro's number. So I'm going to multiply. Because I have molecules here, I want this number on the bottom. So 6.02 times 10 to the 23rd. I'm going to write molecules now because particles is generic. And then I'm going to put the 1 mole on the top. So if you look, I'm going to be canceling out molecules and be left with units of moles, which is what it asked me to find. So on my calculator, I'll plug in 2.0 times 10 to the 19th, and I will divide that by 6.02 times 10 to the 23rd. And my calculator does not give it to me, it gives it to me in fully written out, so it has a 0, and then it has 1, 2, 3, 4, 3, 3, 2, 2, 3 moles. So in scientific notation, it would be 1, 2, 3, 4, 5. So 3.3 times 10 to the negative 5th moles. Now, if you're getting a number that's much larger than that, the exponent, you have the 3.3, but the exponent's the same. When you enter this into your calculator, you need to put parentheses around the entire number in Avogadro's number. Now, the second question has grams and moles. And I know that from my practice that molar mass is what I would use because molar mass has units. It tells me how many grams per mole. So I need to know the molar mass. So the first thing I would do is find the molar mass for CH4. and I would use the periodic table. So carbon is 12.01. Hydrogen is 1.008, and it's going to be times 4, because I have 4 hydrogens here. And then oxygen is 16. And I'm going to add those 3 numbers together. So I didn't multiply the carbon and the oxygen by anything because there was only one of them in the formula. And I get 32.042 grams per mole. So now I'm going to start this like a conversion problem. So I start with what I was given, 0.820 moles, and I'm going to use my conversion factor. So times, I want moles to be on the bottom, and it's always in 1 mole, and there's 0.042 grams. The moles are going to cancel, and I will multiply 0.820 times 32.042, and I get 26.2744 grams. And so to 3 significant figures, I get 26.3 grams. So a generalization here is that to go from moles to grams, you're going to multiply by the molar mass. And that's what I did here to go from moles to grams. Well, let's try another problem. In this problem, I'm given grams and asked to find moles. Okay, so again, in my mind, and I've practiced a lot, you guys know, I know that molar mass has units of grams per mole. And so since it has both of the units that I am interested in, I know that's my conversion factor. So molar mass is something I calculate on the periodic table. So I have to calculate it for sodium chloride. So sodium is 22.99 and chlorine is 35.45. I don't have to multiply them by anything because there's only one of each in the formula. And remember, to calculate molar mass, you simply add up all of the masses of each of the elements in the formula. So I get that this has 58.44 grams for every 1 mole. And that's the molar mass of sodium chloride. So you're going to write down what you're given, and I have 100 grams of sodium chloride. And then I'm going to use my molar mass. Now this time I want grams to cancel. So I say 58.44 grams, and then I put the 1 mole on the top, so grams will cancel. So now I say 100 divided by 58.44, and I get 1.7115, there's 3 ones. 15 moles. Now 100 has a decimal place after it, so let's do 3 significant figures. So I'd have 1.71 moles of sodium chloride. So looking at this, I can make a generalization. If I have grams and they're asking me to find moles, I would have to divide by the molar mass. So I'm dividing by the molar mass when I go from grams to moles. Now number 8, it requires both things. Let's look. So I have grams here and I have molecules. So knowing what I have 2 things I can use when I do these problems. I have molar mass, which has, find on the periodic table, and it has units of grams per mole. So that helps with this number, but this can only go from grams to moles. This problem asks about molecules, and so I remember from my practicing that Avogadro's number tells me I have 6.02 times 10 to the 23rd molecules in 1 mole. And so to get to molecules over here and grams over here, I'm going to have to use both of these conversion factors. Now, this problem really does trick me a little because I'm in milligrams, and notice molar mass is in grams. So let's start by converting the milligrams to grams. I know that there's 1,000 milligrams in 1 gram. So this is 0.325 grams. Okay, so I have 0.325 grams. Now, looking at what I have up here, the only thing with grams in it is molar mass. So I'm going to need to calculate the molar mass of aspirin. So this is going to take my periodic table, and let's see. Carbon, I have 9 of them times 12.01. So let me do it step by step. So 12.01 times 9 is 108.09. And then I have hydrogens, which are 8 of them. That's 8.064. And then oxygens, I'll come down here, which there's 4 of them. Whoops, times 16. So 4 times 16, 64. So now I'm going to add up all of those things together. So 108.09 plus 64 plus 8.064. And I get a molar mass for this, I'll write it right here, of 180.154 grams in 1 mole. Okay, so this has grams, so let's put the 180.154 grams on the bottom in the 1 mole. So dividing, I get 0.325 divided by 180.154, and I'm not going to round this yet, and I get 0.001804012 moles. And then I'm going to take that number, because that is not what I want. And you could do this as a continuous problem like we did in conversions if you wanted. And so here I think to myself, okay, now I have moles. I've already used the molar mass. And now I have moles, and the problem wants me to go to molecules. So I know the relationship between moles and molecules is Avogadro's number. So now I'm going to use Avogadro's number. I'm going to put the 1 mole on the bottom so it cancels, and multiply by 6.02 times 10 to the 23rd molecules. So moles are going to cancel. And so multiplying that number, which I left in my calculator, times 6.02 times 10 to the 23rd, and I get 3 significant figures, 1.09 times 10 to the 21 molecules. So notice when you have to go from grams all the way to molecules, I had to use both the molar mass and Avogadro's number. Now the last part, stoichiometry, really involves kind of both things, using balanced chemical equations and the relationships that you have in a chemical reaction. So the coefficients can tell us the relative number of each type of moles, and so this is very important in these types of problems. So looking at this problem, it says how many moles of oxygen. So here I find oxygen in my equation. are needed to react completely with 3 moles of C2H6. And so I find C2H6 in my equation. So I'm going to write down, you notice there are 2 different things, and it has moles of one to moles of the other. So I write down the one that I know. So I know that I have 3.0 moles of C2H6. Now I'm going to take the coefficients that I have from the balanced chemical equation and make a ratio. So I want to cancel C2H6. So this 2 says that the ratio is I have 2 moles of C2H6. I did not calculate that. I'm simply getting the 2 from here. And then what I'm looking for is oxygen. And I see oxygen has a 5. So the ratio of that is 5 on top moles of O2. So this is called a mole ratio. And it's not really calculated. The mole ratio is determined by looking at the coefficients in the balanced equation. Now I put the C2H6 on the bottom so that it would cancel. So now if I say 3 times 5, and I divide that by 2, I get the answer, which is 7.5 moles of oxygen. So if somebody had 3.0 moles of C2H6, and then they reacted it with oxygen, it would require 7.5 moles of oxygen. Now let's see about the next one, and I'm going to erase what I've written on the first problem because we're going to use this equation again. So here it says how many moles of water. So I'm trying to find water, so I look for water here. So how many moles of water are formed from 0.5 moles of C2H6? So now I'm using these 2 things. And it doesn't really matter which 2 things you use in the equation. You just look at the ones. One you're going to know and one you're looking for. So what I know is that I have 0.50 moles of C2H6. And I'm going to use the balanced equation to find a mole ratio, and that's what I'm going to put right here. So the thing that I'm given is what goes on the bottom, and there's a 2 in front of it. So I'd say 2 moles C2H6. Then I find out what I'm looking for, which is moles of water. And so I go to water, and there's a 6, and what I'm looking for will go on the bottom. on the top. The one that's on the bottom is the one I want to cancel. So see how that cancels out. So now to find the answer, I'd say 0.5, which I was given, times 6 divided by 2. And the answer I come up with is 1.5 moles of water. So let's reread the question and see what we answered. It says how many moles of water are formed from a half a mole of C2H6. So if you start with a reaction and you have a half a mole of C2H6, the result would be the production of 1.5 moles of water. Now all of these different types of equations take practice. And if this worksheet, if you had trouble doing it once, put it down for a while, come back and see if you can work on it again. Also remember there's more in the class practice worksheets under exam preparation, in your homework, in Orion, in your LearnSmart, and in other sources for your different parts in your textbook. You can find more practice problems, example problems in the textbook as well. So there's lots of places to practice. Just keep at it.